Welcome back, ladies and gentlemen. In this video, we're going to be looking at a number of pretty important ideas. Primarily, of course, rotational kinetic energy, but how this applies to energy conservation situations and how that's going to be useful to us when we try to analyze some situations. So to begin, recall that kinetic energy of translational or linear motion is simply 1/2 times the mass of the object times the velocity of the object squared. Well, we also want to connect this to rotation, and there's a really basic way to relate translational speed to rotational, where your translational is equal to the radius times your angular speed, or angular velocity if you like. So we're going to put these together, and what we're going to look at is initially an object that is just a point mass, and this object is going to be a certain distance away from a point in space where we have an axis of rotation right there. So imagine this thing sort of moving around like this. So we do have rotation, right? There is an angular velocity, but there is also this tangential velocity there. And if this is an axis of rotation, then we have a radius or a distance away from that center to where this mass is. And this mass, m, for now, just consider a point mass. So it has no size. Its size and shape is insignificant for our concern right now. So we're going to put these together and apply it to this situation. What we can do is say that, well, the kinetic energy of the rotation, or the rotational kinetic energy, or angular kinetic energy if you like, is just 1/2 mass times, well, instead of a v, we're going to substitute r omega. And that quantity is squared. And so we can sort of just shift a little bit and say that this is going to be 1/2 times mass, and we have r squared, and we have omega squared. And I'm going to put the m and r squared in parentheses here, and there's a reason why. So we can see a couple things. First of all, the kinetic energy of rotation depends on the angular speed, but it also depends on the distribution of the mass. So not only the amount of mass, but where that mass is located. Here we designate that the mass is located a distance r away from an axis of rotation. If that location changes, in other words, if r changes, well, then we would have a different amount of rotational kinetic energy. So what we say is that the rotational kinetic energy depends on the angular speed, but also on the distribution of the mass. And we can look at this and we can say that these, we have two equations. Here's an equation for linear, and here's an equation for rotational kinetic energy, and they are quite similar. If I write them next to each other, there's one, r squared and omega squared, and there's the other. And you look at this, and you have to acknowledge that they are similar. And there's something interesting here. Of course, the v and the omega, your translation or tangential, it is tangential, I suppose, velocity, but also your angular velocity. But more so here, look at what's going on. We have mass here, and we have what we're so far calling distribution of mass here. And this is interesting. So what you're going to want to think about is, for this whole quantity, it has a name, and its name is moment of inertia. Moment of inertia. It's an important term. The symbol for moment of inertia is capital I. Now, this is going to be interesting when we get to other topics in physics. You'll see capital I used elsewhere for other things. You simply must keep it straight what is being represented with a capital I, depending on the context of what you're doing. So, you might think of this as rotational mass. So I'm just going to put rotational mass. That's not a very strict scientific definition, but if you imagine this, imagine trying to hold a long stick by the center and try to wiggle it. Take the same long stick and hold it by one end and wiggle it. And what you should notice is that it's actually easier to change the motion, wiggle it back and forth, holding it in the center. And it's harder to do that wiggle back and forth by holding it at one end. With a pen, it's not so obvious. Take a long stick and you would notice it dramatically. So here's the deal though. Remember that our situation is pretty specific. We're looking at a point mass rotating around an axis, a certain distance away from that axis. So the value of I in this case is mr squared. But you want to make a note that I will not always equal mr squared. It's not a general thing. That is specific to this situation with a point mass. Please, please, please keep that in mind. The moment of inertia, actually has a slightly different value when you're looking at other situations where something else is rotating. Okay, so I just got stymied by my papers. Hang on. Okay, so what we're usually going to do also, and since most of the time, as a general thing, you don't want to write mr squared for your moment of inertia, we'll just write an I in this equation. So we will have the rotational kinetic energy equal to 1/2. I wrote an m. Sorry. 1/2 I omega squared. And this is where I is the moment of inertia for that given rotating object. It is very specific. The value of I changes if you're talking about a different shape and size of an object. For example, if you're talking about a rolling wheel, which is very much like a hoop with a big empty space in the center, compared to a solid disc that is rotating, or to a rotating sphere. All these things have a different value for the moment of inertia. We're going to look at a little bit of that. And then there's also a bunch of the specific details in your textbook. So for the point mass that we were considering, it's located the distance r away from the axis of rotation. For the point mass, the moment of inertia is simply mr squared. No big deal. The precise value does change. Keep that in mind, please. So for example, we'll make that comparison. We have the point mass. There's a center of rotation. There's our point mass. And it's a distance r away from that center, rotating around this way. We could also have, let's say, a rotating solid disk, right? So here's a point mass. could have a disk. And a disk really is equivalent to a solid cylinder. Okay, so bear with me as I try to draw this. And back, okay. And try to give it a bit of perspective here, three-dimensionality. Okay, hey, not too bad, right? And a little bit of extra detail here. So we saw the rotation here with the point mass, and essentially the axis of rotation is coming out of the page toward you. Here the axis of rotation is basically through the center of the disk, right? And so rotation happening like that. And there's also a radius that we can identify. There's a radius right there. Now we can also think about a hoop or a ring. This would be sort of similar to a bicycle wheel, or any similar type of object where the central region of the object is open and empty. So this guy is solid material all the way through the center. We're going to try to draw a hollow hoop. Let's see if I can get this guy going. This will be interesting. I don't know if I can do this accurately, reasonably. Kind of get skinny there. I'm trying to give it some perspective. A little skinnier. Well, it's pretty terrible, but bear with me. And now the hoop can have sort of any dimension this way that you want. It's still empty in the center. So for example, a bit of this to give you that illusion, right? And there's an axis of rotation basically through the center. And we can just indicate rotation about that axis here. Now there also is a radius, right? So we have a radius here. Awesome. Oh, I forgot the label on that guy. Hoop or a ring. Or you might think of this as like a cylindrical shell, right? If this is a solid cylinder, this is an empty cylinder. You can see that radius is involved in all of these. Radius does matter, but so does where the mass is located. The moments of inertia for these three shapes, I'll show you this real quick. This one for the point mass, you already saw, mr squared. For the disk or solid cylinder, the moment of inertia actually has a value of 1/2 mr squared. And for the hoop or the ring, the moment of inertia has a value of, well, again, it's interesting, mr squared. Essentially, what the hoop or the ring is a whole series of point masses that are all equal distant from the center of rotation. So there's a little tiny bit of the hoop or ring right there, and there's all sorts of other tiny bits of the hoop, and they're all the same distance away from the axis of rotation. And it's interesting if you count bits horizontally this way. Well, they're all the same distance from the axis of rotation. And the wider it is this way, well, you're just increasing mass. And if you think about this is just one bit, and it's only, so it's not a continuous hoop, and it's only one bit sideways as well. So you'd have a much smaller mass here typically than you would here, and therefore your moment of inertia ends up being different, and it all works out. There are numerous other examples of other types of shapes in your textbook, so check it out. These are three common ones, but they're not the only ones you'll have to be able to use. And I would suggest you start practicing these things, maybe even memorize them for your own benefit to make this kind of work much easier. You're going to want to be able to recall these pretty quickly. So now here's the thing. What is the significance of the moment of inertia? Why is it important? Why does it matter? So if you look at the equations, you can see mathematical relationships. It essentially plays the same role in rotational motion that mass plays in translational motion. So if you recall the equations for kinetic energy, there's translational and then rotational, right? Then moment of inertia plays the same role that mass does in this relationship. The larger the moment of inertia, the harder it's going to be to change the angular velocity of an object. It resists those changes more. And so again, practice getting that stick to wiggle, hold it in the center, hold it at the end. By moving the location of where you hold it, right? Imagine holding the stick in the center and try to change that angular motion, and then hold the end and try to change the angular motion. By moving where you're holding it, you are actually changing the moment of inertia of that object. And you'll notice it's harder to do that. With a larger moment of inertia, it's harder to change its motion. It's harder to change its angular velocity. Now, let's get to how this applies to conservation of energy. Right. So we want to look at what the kinetic energy of a rolling object is going to be. With a rolling object, you have both translation and rotation taking place simultaneously. So the total kinetic energy of a rolling object, where there's no slipping, it's pure roll. Well, we're going to have the translational component of that kinetic energy there. But we are also going to have the rotational component of that kinetic energy there. It's just the sum of the two. Now we can substitute in here for omega for angular velocity. Well, that's just velocity divided by radius. So a quick substitution here, and we start to reduce the number of different variables in the equation. And in your textbook, it does something interesting with this bit. I'll show you where it goes, and then I'll try to explain it for you. It actually does make sense when you dive into it. You end up with 1/2 m v squared. And essentially what we're doing is we're factoring out a 1/2 mv squared from both of these terms. So I'm going to end up with 1 plus whatever's left over here. Now in this side, when I factor out a 1/2 mv squared, I need to recall regarding moment of inertia, I'll put this off to the side for you. Moment of inertia for various objects is just some constant multiplied by m r squared, right? And so that constant itself, if I divide both sides by m r squared, that constant is moment of inertia divided by m r squared. Now I won't know what that constant is. That constant changes from one type of shape to another. And so I really can't use that. But listen, The way I've done this is, instead of having to know that, I can simply work with this. That constant depends on the distribution of mass, right? But if I view it in a different way, you might see this a little better. I'm going to say that when I factor out of this term the 1/2 mv squared, I am left with moment of inertia divided by m r squared. I'm left essentially with that constant. And now, if you're unsure of how that comes about, you're welcome to come and talk to me. I can sort of work through it with you. It's not a terrible deal. How you get there is not so critical. But what's interesting is just that, well, now we only have a mass in both places. We have a velocity here, we have a radius, and we have a moment of inertia. And it gives us something we can work with. So let's look at this. So how do we apply this idea to conservation of energy? Well, let's take a look at an example where we have an object that's going to roll down a ramp. And this object has a radius r, and at the end of the ramp it's rotating, and we're going to let it go from rest up here at the top of the ramp. But as this object at the bottom is rotating, it's also translating. So there is a velocity here, and I want to know what this velocity is going to be. That's my goal. Okay. So there's some information we're going to need, right? Or at least look at. I know that starting up here, there's no motion taking place. We're starting from rest, but we're starting at this height above the ending location. So with this height, we've got gravitational potential energy and down, but no kinetic energy, either rolling or translating, none at all. It's at rest up here. And down here we've got no height left over. We're at our 0 reference line, but we've got both rotational and translational kinetic energies. So energy will be conserved. We have the object allowed to roll down without slipping. Starts at height h, finishes at height 0 at our reference line, and we want to find that final speed at the bottom of the ramp. Since energy is conserved, mechanical energy initial is equal to mechanical energy final, and so mechanical energy breaks down into kinetic and potential. So the sum, that's an F. The sum equals the sum here. But initially up here there's no motion at all, so that goes to 0. Here this is pretty easy. We're close enough to Earth's surface. We're not using the universal law of gravitation. We're just going with G equals to 9.81. So we get to say that mg y, where y is the vertical change in position there, right? Well, at the end, this kinetic energy now is going to be the total kinetic energy of the object, both rotational and translational. So we get to use this equation. And so 1/2 mv squared multiplied by 1 plus moment of inertia divided by radius times mass squared. Sorry. Oh. Yikes. Yikes. Erase that guy. How about we do mass times radius squared? That looks much better. Sorry about that. Brain's not working as fast as the pen is. So, but this is only the one term, right? That gave me this guy. That gave me this guy. This gives me that whole thing right there, the whole deal. And so this potential energy must give me some other term. And, well, if this is now at the reference line down here at 0 height, then the potential energy will be 0 at that location. Okay, so simplifying this, and ultimately what I need to solve for is going to be this velocity. That's what I want. That's my goal, right? So here we go. I'm going to spare you some algebraic manipulation. It's a good exercise to work through, but I want to save time here in the video. So we end up with 2gy divided by 1 plus I over m r squared. And the whole thing is under the radical. Sorry, my radical didn't quite go down far enough. There you go. Okay. So this is interesting. This would allow us to find that velocity at the bottom of the ramp. And it turns out, if we know the moment of inertia of this object, if we can determine its shape and its mass and its size, we can work out this final velocity quite handily here. And it's not a problem because we've incorporated both the loss of gravitational potential energy, giving it translational energy, but also giving it rotational energy. But the velocity here is only accounting for one of those types of energies. Now, there's something that you should be thinking about. Looking at this equation, you should be reminded of something. Why does this equation resemble something else that you've studied? Why does this equation resemble this one? Well, think about this. If your moment of inertia is 0, then what happens to this whole little bit right here? Well, that goes to 0. 1 plus 0 is just 1. You're dividing by 1, so it turns into that. If this object were not rolling down the ramp, if it were sliding, purely sliding down the ramp, well, that would make a lot of sense, wouldn't it? Then it would have picked up a velocity dependent upon how the vertical change in position here, and dependent upon the gravitational acceleration. But that's if there's no rotation. So you'd have essentially moment of inertia is 0 with no rotation. So that's interesting coming out of this this situation where you have that sort of similarity. But you can see that with rotation we have to throw in the extra term to account for the discrepancy that we would see. If we worked out velocity this way only, then we would not be accurate, right? Because this thing is rolling. There's rotational kinetic energy here as well, which will make this not a valid, not an accurate means of finding the velocity. Well, okay, this works also for an object that is rotating due to winding or unwinding of a string. Object like a pulley with a string or a rope around it, or an object like a yo-yo. So this kind of thinking will work there also. We will use this type of thinking here, not necessarily that same equation, although we might. So here's what I want to look at. I'm going to check out an Atwood's machine because this is very common with a pulley. There's a center and string coming down to a mass hanging there, string coming down to a mass there, and this mass is starting out on the floor, the table, whatever that surface is, and this mass is M1, M2. M1 is starting out a certain vertical distance above that surface. Okay, this pulley also has a radius R, right? And the way I've drawn it, you can already see that M1 is larger than M2. So when released, you know that M2 is going to move up, M1 is going to move down. and the pulley will end up rotating. So in this example, though, let me be specific here for you. We're going to release it from rest. So just jotting down some basic information. Release from rest. The two masses, M1 will be 5.0 kilograms. M2, let's 3.0 kilograms. Let's make the height of M1, the initial height of M1, 3/4 of a meter, 0.75.